I'm Andres, I'm at King's College London, and I work in the T2K experiment, which is a long baseline oscillation experiment. So none of what I'm going to say is specific necessarily to the T2K experiment, but I'm going to use it as an example to set up how these experiments work in case you're not very familiar with that. So hey, there we go. So this is a little diagram of a T2K experiment. So this is clearly a Japanese diagram because the neutrinos come out from the right side and go towards the left side. We would usually have done it the other way around. But essentially, we have an accelerator there in the JPark site, and then we have some mirror detectors, several actually, that try to measure the neutrino flux at the reactor. And then the electroneutrino flux or antineutrino, we have some foreign currents and whatever. And then we have a far detector some 300 kilometers away that measures both the electron type flux and the muon type flux. And we do this through discrimination via Cherenkov radiation. But again, that's not the important thing in this talk. The whole point is that we can measure the ratio between these two fluxes. And in the vanilla case, where there's nothing weird happening, this should be essentially the probability of transitioning between the two flavors at our baseline and at our energy. So yeah, that's what Joachim was talking about this morning. So I'm not going to bore you with this too much. Essentially, we do have this change of basis matrix. So that's important because we know a lot about change of basis and about vector spaces. And if we assume we have 3 neutrino states, this is going to be some complex matrix where the real part is SO3, which is isomorphic to a solid sphere, which may become important later. And yeah, we need to understand our spaces in order to understand our oscillations, because in the end, they are pertaining to all these very structurally sound mathematical objects. So the Pms matrix, it's again, we've talked about this already. We usually parameterize it as a product of these 3 rotational matrices up there, with some complex phase attached to them. This is what it looks like once you do the parameterization. You may notice that there's 5 elements that have the complex component attached to them. The top rightmost, and then there's the square with 4 of them, which we call the compound elements because they have both a real and a complex part. And here we start seeing some problems because, of course, the position of the imaginary parts in the matrix are up to our parameterization. And in fact, there are 9 matrices that will give you the exact same oscillation physics. There's a 9-fold degeneracy. We choose this parameterization because of the smallness of this top right corner element. I'll talk a bit more about that. But essentially, we choose these angles because they're useful, but we shouldn't think of them necessarily as angles. This is a parameterization called the Tate-Bryant parameterization. It's an atlas onto SO3 with this appended phase, and there's essentially 9 possible ways of doing this. We chose, again, the one that satisfied our requirements for the smallness of that element. But just think about this. We could create a different matrix by multiplying these 3 matrices in a different order. It would still be a valid matrix. It would generate the same oscillation physics, but everything would work differently. The angles would mean different things, etc. So my research is precisely about questioning this kind of assumptions we make and how these questionings might affect oscillation analysis. So a bit on the usual paradigm, we use a small angle approximation to figure out what these angles mean. Essentially, we're taking SO3, which is a solid sphere, assuming that one of the angles is really small, and that contracts the sphere into a spherical shell, which is isomorphic to S2. If you don't like topology, I completely understand. Good for you, honestly. But essentially, S2 is more similar to S1, which is the case of the 2-flavor approximation. And in this case, you can ascribe value to the angles. SO3, different beast altogether, shouldn't be described in terms of angles. And that's why we have a very nice solar angle, a very nice reactor angle, and then we have some third angle that we don't really know what it is. We usually don't talk about it because we do the small angle approximation. And it's because they're very different things. And yeah, let's try to figure out what. Usually in long baseline oscillation, we do some sort of analysis. In my case, a Bayesian one, where we take our data, we shove it into some 3x3 unitary matrix fitter, and we come out with constraints for our 3 angles and our complex phase. But you can't just do that. You need to think about what you're fitting. in our case, we're not fitting fundamental objects, we're fitting some elements of some parameterization that we've chosen. And these things need not be, for example, uniformly distributed over our space. So in the case of some Bayesian statistics, you're going to have to think very carefully about your prior distributions underlying your parameter space. In the case of frequentist approaches, you might want to think about which variables you do your chi-square minimization on, or if you want to put some correction factors, etc. So let's look at that. First of all, my talk is about reparameterizations. I've already mentioned some ways of parameterizing the matrix in similar schemes, but of course, reparameterizations also allow us to look at just different spaces. The Tate-Bryan angles, or the Euler angles, as you might have heard them be called, are parameterizations of the U3 matrix group, which is where we assume that PMNS is if we only assume normal oscillations. And well, the PMNS is actually in a smaller subset of U3 because, as you know, it only has one complex phase. U3 in general has 9 complex phases. So it gets a bit more complicated than that, as always. But essentially, we can use different parameterizations for lots of different things. In the case of sampling our space, there's the Tate-Bryan parameterizations I talked about, and then there's something called the anarchy sampling, which is very popular nowadays, and it's due to something called the Har measure, which again, I don't have time to explain, but you can ask me about it if you like group theory. And then we have all this really fancy stuff like non-unitary parameterizations. Thomas Swartz has his T-symmetric parameterization, which doesn't assume the nature of the CP violating part in neutrino mixing. It's really interesting. Then you can do Har SO3 samplings if you don't assume CP violation, and then you get a different distribution for your angles. But for time reasons, I'm going to focus on this, which you might not care about that much, but again, it's what I care about, and I'm the one speaking. So as I already mentioned, we can write down the SO3, which is the real part of the mixing matrix, in terms of 6 or 9 if you're repeating the matrices, but let's not get into that. Different ways in terms of 3 angles. And the usual parameterization takes advantage of the fact that the top right corner element is really small. And due to very deep topological reasons, there's always one parameterization that's going to abuse that to give very nice features. But we shouldn't be assigning any kind of special value to this parameterization. It's a useful one for small angle approximations, but nowadays we've got the sensitivity where no one really does small angle approximations. We fit the full 3 flavor oscillation paradigm, so there's no reason to just value this parameterization over the other ones. So this here is an example of what different samplings look like in our usual space. This is the CP violating phase in the usual parameterization. Again, the CP violating phase also changes as you choose different parameterizations. And all these are distributions which are flat in their respective parameterization, and of course are no longer flat in our usual one. So why should we assume that the CP violating phase is uniformly distributed? Well, we shouldn't. In fact, once you run an analysis, you should make sure that your results are invariant under the choice of all these different underlying distributions. And only then you can actually claim some sort of results. And that's exactly what we do in T2K. So in order to understand what the hell is going on with these parameterizations, I cooked up this little Tix figure. So these are actually all characters. They're not drawings. So I spent a very long time LaTeXing that. But essentially, we can try to visualize why these things are not angles. And the way I think about it, imagine this is the 3x3 mixing matrix. We have the columns here, which represent the mass eigenstates. We have the rows that represent the flavor eigenstates, right? And each point is going to be the inner product between its respective column and row vectors, right? So in the case of the nominal parameterization, which is the ABC one, because we multiply matrices A, B, and C, we've got the top right corner is just the sine of the theta 1,3 angle. So what does that tell us? That tells us that the sine of the theta 1,3 angle squared is just the inner product between the M3 state and the electron state. So these states, they're normalized. So they have a length going from a length of 1. If they're perpendicular, their inner product is going to be 0. If they're the same, the inner product is going to be 1. So we have a number that goes from 0 to 1. And we've somehow said, OK, well, let's take the sine of some angle between 0 and 2 pi and say, well, that's a number between 0 and 1 as well. So we're going to use it to parameterize our matrix. It's a bit ridiculous. This is not a real angle, and we shouldn't think of it as such. Therefore, if we make some sort of distribution for this, we should take in account that it's an inner product and make the distribution on the inner product, not on the angle. Now, for the remaining two angles, I like to call them the flavor ratio and mass ratio angles. And that's because the tangent of the theta 1, 2 angle is actually the ratio between the first two columns of the Pms matrix. And the tangent of the theta 2, 3 angle is the ratio between the last two rows. So in a way, they're telling us about the ratio of the contribution of two mass states to the flavor states and two flavor states to the mass states. And then the CP violating phase tells you about the diagonality or anti-diagonality of this square over here. I said a lot. I know it's a bit hard to take in, but essentially the reason why we don't really understand naturally what the theta 2, 3 angle is because it's giving us a ratio between contributions of flavor states to a mass state. And we can't measure mass states directly. We can only measure flavor states in our detectors. So we can't just directly measure the contribution of flavor states onto a mass state, because we would have to look at some appearance or disappearing channel between mass states. And we can't do that. We can only do flavor states. So that's why it's a hard angle to determine. For the 9 different parameterizations, essentially, they're uniquely defined by where you put your angle that represents some inner product. So in this parameterization we use, the nominal one, we choose this very small element over here. If we were to choose, for example, the central element, then the mass ratio angle will tell you the ratio between the first and last columns, and the flavor ratio angle will tell you the ratio between the bottom and top rows. So you can imagine how you generate all 9 in terms of this interpretation, and everything becomes a bit more intuitive, in my opinion. And it also sheds light on this last one thing I would like to talk about, which is that the delta CP is not really a good measurement of CP violation, because again, it only tells you about the diagonality or anti-diagonality of the adjugate parts of this matrix. There's something called the Jasper invariant, which is becoming very popular nowadays, and many oscillation experiments are actually giving the results in terms of the Jasper invariant. And this is something that was invented by Cecilia Jarskog for the CKM matrix. And it's a parameterization invariant that tells you the scale of CP violation in any kind of mixing paradigm. And I don't have time to talk about that a lot either. So let's just brush over this Har sampling that I was talking about. Essentially, these elements, this Pms matrix belongs to some group, which is a space and a group at the same time, so we call a Lie group. And these things have a lot of structure, and we can abuse that structure to get some sort of uniform sampling out of them. So for the U3 group, which is where we assume usually the Pms matrix will lie in, you get one sampling. If you assume that the Pms matrix doesn't have a complex part, you have to do it in the SO3 group, and you get a completely different sampling. And this is what it looks like in terms of the mixing angles, complex phase, and the Jasper invariant. And this is the same for the SO3 case. So as you see, these things are not uniformly distributed. You can see that the inner product angle is differently distributed than the ratio angles. So yeah, I think this is all very interesting. And if you want to look more into it, you can look at anarchy samplings. I think Tepe and Carlos are really interested in this kind of things, and they've written some papers about it. And finally, so what does this actually mean for oscillation physics? Well, these are sensitivity results. It's not real data. But what I've done here is I've taken all those different distributions I showed earlier, and I applied them to this fake data study on the T2K oscillation data. And what we find is that the contours don't actually change much for all these different hypotheses of underlying distributions. In fact, it seems like our nominal parameterization, which is the shaded region, already gives us the weakest discrimination of no CP violation. So it's like the most conservative case, which is very good news. But the fact that we lucked out in this case, you can see here even the octant discrimination doesn't change much in theta 2-3. The fact that we lucked out is good, but it doesn't mean that we shouldn't be doing this for lots of different experiments. So my takeaways are the following: study your underlying phase space for intrinsic structure. If you have some phase space that is very mathematically sound, you might want to make sure you're not parameterizing it in a crazy way, especially if what you're measuring is not an actual physical thing, but some parameter. Do not attach value to purely mathematically motivated parameters. Again, these angles are very useful because we can do small angle approximation, but they don't mean anything. The CP violating phase is very useful because it allows us to quantify CP violation in terms of phases that are very nice in our quantum mechanics paradigm, but they don't mean anything. And while in neutrino analysis, this falls in very tightly because we can't actually directly measure all the things we want to measure. But luckily, our results seem to be robust enough. And yeah, make sure you understand the assumptions behind your choice of parameterization, because sometimes you might be thinking you're giving freedom for, I don't know, non-unitarity, and then you do your unitarity triangles and misunderstand what experimentalists are doing. So as theorists, please make sure you understand what kind of fit experimentalists are doing before using their data. Don't have time to get deep into this, but I've seen some really, really, really worrying papers where they seem to really misunderstand what's going on in Nova and T2K. But yeah, thank you very much. I think that's all from me. If you have any questions, please feel free to ask.
Other questions? Yeah.
Hi. I was just wondering if you want to do this kind of analysis, considering Majorana neutrinos, where you have these extra Majorana phases, how it would, which would be the challenges you have to face for this extra?
The Majorana phases cancel out in neutrino oscillations.
Yeah, I know for neutrino oscillations, but in general, I mean.
Oh, in general. Well, yes. The Majorana phases have. Do you know what unitarity triangles are?
Yes.
Great. So Majorana phases essentially just rotate the unitarity triangles, right? So what you have to look at, this in some way are real rotations. So you kind of get away with having uniformly distributed phases. But that just happens to be because we're lucky enough that our mathematical paradigm is very near what's actually happening. In the case of the general U3 case, the complex phases are always uniformly distributed. And this is because due to some isomorphisms between U3 and certain matrix groups. But in general, yeah, in the Majorana case, you're free from this kind of trouble. It's when you have mixing phenomena where you're taking matrix groups and trying to parameterize them in terms of purely real elements, where you start getting all this nasty behavior.
Okay, thank you.
So, yeah.
So maybe in your slide 17, I think. So you did mention about the Asimov true values, and you for your simulations you use the Asimov case. But why not the Monte Carlo case? Or like, will it not fit better into the parameters?
Asimov is just you choose a set of true values, and then you run your Monte Carlo, assuming that those values are.
But Monte Carlo is not Asimov.
Right, but so in an Asimov fit, you choose certain values as if they were the true values of the universe, and then you generate fake data using those values, right?
Yes.
And then what we're doing in this case is an MCMC analysis on top of that. For Monte Carlo, you still have to choose certain underlying parameters to define your theory, right? Or else you're not going to have an algorithm for running your Monte Carlo. So sure, you can choose different values. In this case, like, this is not a fit. This is underlying distributions. So it doesn't really matter. It's just an eye guide for what our nominal values is. By Asimov, the Asimov A2021 of T2K is just the new fit best fit point. So essentially, it's telling you whether our best fit value for the angles looks natural with respect to these distributions, or if it doesn't.
So what I wanted to know, why is it better? The Asimov thing is more better and more preferred in your case, because there are also multiple ways. Like in the Monte Carlo random generation, you can also fit the parameters to fixed and free values.
But I'm not fitting anything.
Okay. All right.
Right. I mean, here this is a fit, but this is just a sensitivity fit, right? So the reason why we use an Asimov is just because we want to test what our discrimination would look like if these were the true values in the universe, right? Oh. And of course, there's lots of Monte Carlo involvement in this because we have to simulate the sensitivities, etc. But yeah.
But we're generating a model and we're fitting the data to that model, right?
Yes, exactly. But the model we're doing is precisely this. So this is independent of whatever you're doing in your actual specific oscillation experiment, right? This is more going towards your model of whatever you choose your mixing matrix to be.
Okay.
So the idea is that this parameterization works for the normal free flavor analysis. Yeah. If you were to choose a different model, maybe your matrix space is different, and then you have access to different parameterizations. But for example, this kind of Euler angle or tape variant angle parameterization assumes no strong neutrinos, no
Can you go back
no
to the
interactions, etc.
the sensitivity plot?
The sensitivity plots. Yes. So these are sensitivity plots for T2K 2021 in the normal vanilla case.
Normal hierarchy, I guess.
No, integrated over both hierarchies.
Integrated
Yeah.
over. Okay. Okay. Okay.
Yeah.
So you are marginalizing over the hierarchy. Okay.
Yes, exactly. It's marginalized.
Okay.
dimensional
Okay.
consistency.
Okay.
And I have a plot, I think, somewhere for both hierarchies, but this doesn't really affect the hierarchies because the masses are real parameters, so they're not really affected by your choice of parameterization.
Okay. Okay. Thank you.
Okay, I would like to suggest that we continue discussions during the coffee
Mhm,
break.
yeah.
So let's thank Andres again and everyone in the session.